Oh no. All right. Hey everyone. Welcome back and welcome to Unit 4 of AAF. So, Unit 4 of AAF is our study of quadratics. So, if you remember, hopefully, Unit 1, we focused on functions, right? And we did like function operations, function notation. What is a function? We looked at inverse. We looked at a variety of different things, domain, range, those characteristics of functions. And then in Unit 2, we really focused in on linear functions and linear equations. And part of that was piecewise linear functions, which was absolute value. We then dove into matrices, which, as we hopefully saw, related pretty closely to linear functions. There was some commonalities in that, and we did some study. We did work with matrices, and now Unit 4 is quadratics. So you did study quadratics in Algebra 1 and a little bit here or there in geometry, but really in Algebra 1, and you had that's really where your foundation was built on quadratics. So there's a lot of things throughout this unit that you will see and we will work with that you have seen and worked with in Algebra 1 in the past, and that's good. That is the place that we want you to be. And we want to do some review, and then we really want to build on your understanding and your knowledge. So if there's things that we talk about that maybe we mentioned that you learned in Algebra 1 and you're having some trouble with it, just make sure that you're seeking out the support early and not waiting until you're in over your head. But if you do have a recollection of this stuff, awesome. It is a lot of Algebra 1 review. Just amped up a little. So in this first lesson that we're going to be working with in Unit 4 of quadratics, we're going to extend our understanding of the number system. Remember, we did the number system to define complex numbers. Hey, wait a minute. Complex numbers? Wasn't that just all numbers? So that's interesting. We're going to define more specifically complex numbers and then use our algebraic knowledge to add, subtract, multiply, and divide, and simplify a variety of complex numbers. Okay, so we're going to do some basic operations with these complex numbers. Okay, so this is a little silly, but I'm going to show you a video within my video because I thought this was a really good introduction to imaginary numbers, right? We've really talked a lot, and if you remember, we had complex numbers were at the very top of our tree. And then from complex numbers, you could have real or you could have imaginary. And you've really lived over here on the real number system, right? That's your previous study of quadratics, and really everything else was about the real number system. And as we've talked about, IB and just in general, you're going to default to the real number system unless it says otherwise, right? So here's where we're really going to build our understanding of imaginary numbers.
We already know what real numbers are. These are the numbers that can be represented on the number line. We also know that real numbers can be broadly classified as rational and irrational numbers. Rational numbers are those that can be represented as ratio of two integers with no common factor. Irrational numbers, on the other hand, cannot be expressed as ratio of two integers, and when expressed in decimal notation, they are non-terminating, non-recurring decimals. Are there any other kinds of numbers? Numbers that we haven't looked at yet? Before you answer that question, let me ask you another one. Can you think of a number which when squared results in a negative number? Yes, a number which when multiplied with itself gives a negative number. Try it. You'd have probably tried a few options. 3 times 3 is 9, positive. Negative 5 times negative 5 is 25. Again positive. Negative root 3 times negative root 3 is 3, positive again. No luck. We'll come back to this. Don't worry. So we've studied quadratic equations in middle school. We know that if x squared minus 9 is equal to 0, x is either equal to 3 or negative 3. Now try to find a solution to x squared plus 1 equal to 0. Not sure? Or do you think there's no solution to this one? Don't worry if you couldn't get the answer to these two questions. Let's understand the situation now. Whenever we considered the square of a number, say x, the result was always positive, whether the number x was a positive real number or a negative one. We always got a positive result. And we had learned that a negative number did not have a square root. So if we had a number like -9, we said that its square root did not exist. Do you remember that while finding the solution of a quadratic equation using the formula, if the discriminant b squared minus 4ac was negative, we said that there are no real roots of the quadratic equation. Based on what we had studied earlier, x squared plus 1 equal to 0 will not have any real roots as the value of discriminant is -4. Why did we do this? What was the problem here? It's easy. As the square root of -1 did not exist for us, we said that there was no solution for the equation x squared plus 1 equals 0. However, in the 16th century, it was a mathematician named Cardan who first started thinking about solutions of quadratic equations with negative discriminants. Soon, others started too, but it was Euler in the 18th century who gave the square root of -1 a symbol I and called it the unit imaginary number. These were termed so as they were thought to be impossible and just something we imagined. So I was assumed to be a number whose square is -1. Now you'll be able to answer the two questions. Can you think of a number which when squared results in a negative number? Yes, it's I. If square root of -1 is I, what is I times I or I squared? It is root -1 times root -1. That gives us -1. There you go. We got a negative number by squaring a number. And the next question was, can you find a solution to x squared plus 1 equal to 0? The answer is yes. Transposing 1 to the right-hand side, we get x squared as -1. Taking the square root on both sides, we get the value of x as root of -1 or minus root of -1. That is plus minus I. So what we learned in school wasn't incorrect. This equation has no real roots. Yes, it has imaginary roots. That's the concept of imaginary numbers for you. But wait, we understood the concept of square root of -1. What if the number is square root of -7 or square root of -9? That's what we will cover in the next video.
Right, pretty great. Right, so it gives you some background and a little bit of information about extending your understanding of the number system of things that we concluded just had no real solution. It's not that they don't have a solution, period. It's they don't have a real solution, right? And what you know as real numbers are, think about a number line that you've maybe seen on the board since elementary school that your teacher had above. I don't know, it's hard to picture now. I'm having trouble. That had above like a bulletin board. That is the real number system. The imaginary number line is something different, right? And we're going to take a look at that as well.
Understood the concept of the
We don't need
unit
to watch it
imaginary
again.
number I.
Very sorry.
It is the square root of...
Okay, there we go. So I want to give you a little bit, before I go to more into this and summarize it, I want to give you a visual on GeoGebra. And again, this is going to go a little bit maybe beyond what we need to know, but I still think it is really good and useful for us. So here on GeoGebra, I have what might look to you just like a graph. And maybe, I don't know why I'm saying maybe, hopefully over here you see some stuff written down. I don't like how I drew that. Let's go back. Right, so I see like 8 plus 5i. And I see 7 plus 2i. And then I see a bunch of different operations down here. Now, I haven't even talked about operations. I haven't even talked to you yet about what a complex number really looks like. Right? And so you can see I have 8 plus 5i. Well, check this out for z. Oh, this is a vector. Oh, maybe think about how that relates to what we just studied with matrices. I talked about vectors before. So again, I'm a little bit beyond what you might need, but it's still good to get that visual. So 8, I'm going over 8, and then 5i, I'm going 5. Well, there's an imaginary part. So what happens? What happens if I just drag this over to here? So as I do that, you can see like what's happening with the real component and the imaginary component, right? So what I actually have here is this number line that you've always known doesn't change. This is the real number line. This is the imaginary number line. They're perpendicular to each other, right? So if I just have a number, let's say I pull my vector just along the imaginary number line. Well, it's just pure imaginary, right? If I go the other way, what's going to happen? Oh, it's going to become negative. It's pure imaginary. When you start going out, when I go along the real number system, real number line, it's just pure real. There's no imaginary component. When I go somewhere out here, no matter which quadrant or which part I go to, I end up with both a real and an imaginary part to this number. This is what a complex number looks like. It's a plus bi, where a is real, and then bi is the imaginary part. So it has a real component and an imaginary component. That's what an a and b are just integers, or real numbers. I guess they don't have to be integers. Yeah, they certainly don't have to be integers. Sorry, did not mean to say that piece of it. So this is complex, right? That's a number, and that's how every number can be written. And you might be wondering to yourself, or thinking to yourself, well, if I'm saying every number is complex, how is the number 2 complex? Well, this gives you a visual of it. So if I just go to 2 on the real number line, 2 plus 0i, it can be expressed that way. Not often, right? Like you've never maybe seen that before, but it can be expressed that way. And same thing if you're dealing with something that's just pure imaginary, like up here, that's 4i, but it can be written as 0 plus 4i. It's kind of like when you learned about rational numbers, and 2 is a rational number, even though it's not a ratio of, you don't see it necessarily as a ratio of 2 integers, but it can be 2 over 1. So let's say I've got these 2 vectors now, these 2 complex numbers. And let's say I add them. This is kind of a cool visual. Oh, see that? I shifted that up and I did that. For those of you that are interested, you might want to think about magnitude and direction. I'm getting way ahead of myself now. This is you'll learn this later on. But if you're really interested, magnitude and direction, maybe you want to look into more about that and see what the relationship is. So when I add these two complex numbers, right, 5 and 7, I get 12. 7i and 2i, I get 9i. So I'm 9 now on the complex number line. I'm sorry, on the imaginary line, and I'm going 12 on the real part. You can kind of see where that's coming from, right? It's like you're just shifting that up. It's like I'm going there, and then I'm adding that on. Well, what happens if I didn't subtract them? Let's say I was gonna, add them, I was gonna subtract them. So now I'm shifting it there, but I'm also like reflecting it or rotating it. So I'm going in the other direction, like I'm going out that way and then whoop, back. And that's where I end up. So 5 minus 7 gives you negative 2. 7 minus 2 gives you 5. What if I went the other way and I did w minus v minus z? Ooh, right? So I'm going now this way, and then I'm going to go back that other way. Like, right? So it's like where this points, where this ends, the next one starts. So I never have like the arrow pointing the arrow. But if you multiply them, oh, that becomes pretty far. Whoa, whoa. Right? So I end up with a 59 at the end of that. Is that right? 59? I think so. Oh, I think it's right here. I wrote over it and I can't even see it. Sorry, guys. Right? Yeah, 59i. So I must end up. So think about how you multiply these. Well, maybe you remember multiplying binomials. That relates. We're going to talk about how you do all of that in a moment. I just think this stuff is so cool. And then I can also do z divided by w, and I get little. Z divided by w, and you can see it's 0.92 plus 0.74i. So it's very little. And then I can go the other way and do w divided by z. which you can see what I have there as well. Okay, so just to kind of link it back to some things that we studied and some things that maybe you will study. So complex numbers. I just kind of define these, but just to give it a more formal definition, a plus bi or a minus bi, right? It's one number. I'm not talking about two numbers here. It's a plus bi, a minus bi. Can't combine them. They're like not like terms. A and b are real. So 3 minus 2i is a complex number. 3/5 plus 2/7 is a complex number. 9 is a complex number, right? That can be 9 plus 0i. Negative 2i, right? I could have 0 minus 2i. And the operations that we're going to talk about are adding, subtracting, multiplying, dividing, and simplifying. So the definition of I. So I, as that video talked about, is the square root of -1. It's an imaginary number. It is not real. It is pure imaginary. Therefore, I squared is -1. This is a real number. This is real. If you have a negative under a square root, factor out the -1 and simplify. Okay, the square root of -25 is the same thing as -1 times 5 times 5. Therefore, it is I5 or 5i. Be careful though. If you see it written like this, oh, this shouldn't this be, never mind. If you see it written like this, you have to simplify before you multiply. Okay, if I go ahead and I did this, that would mean I have the square root of 25, but I clearly know I have two imaginary numbers, right? So if a and b, the square root of a and the square root of b are both real numbers, you're fine. This rule works where you can combine them, but if they're not both real numbers, I can't do that, right? This is what I would end up with. I would need to know that this is -1 times the square root of 5. I'm sorry, the square root of -1 times 5 times the square root of -1 times 5, which is the square root of -1 is I. The square root of -1 is I. So I need to break it up like this. That would then give me, oh, sorry. Thought it was written there. My bad. I times I, which is I squared, times the square root of 5 times the square root of 5. Then I've got the square root of 25. I squared is -1 times 5. I get -5. Whereas here I would have gotten 5. So here I was incorrect. So you need to be careful with that. That only works if you're just dealing with real numbers. Just simplify before you multiply. What about this one? Or this one? Or this one? Maybe you want to pause the video and try them out. Simplify first. The square root of -25 is 5i. The square root of -9 is 3i. So I've got 15i squared, which means that I have, this is just -1, means it's just -15. What about this? Here I've got, I'm going to simplify before I multiply. I root 2 squared, and then I'm going to go ahead and distribute that squared. It's going to give me I squared times root 2 squared, so 2, which gives me -2. So this one, I guess I could have thought about it and said, well, the root -2 times root -2. Oh, it's a -2. Miss Gallen. I knew something didn't make sense. Oh, no. No. I was fine. This isn't a -2. I'm all over the place. This is just a 2 because I factored out that -1. Right? So here I could have said the square root of -2 times the square root of -2. I'm not going to multiply them out, but I'm going to know that if you, like, these operations are going to cancel, I'm just going to get -2. So if you recognize that, amazing. Right? It's just like if we said the square root of 5 squared, you get 5. They're inverse operations. What about this one? So let's multiply the numbers in front. Let's simplify all of this. So I've got 3 times 5i times -2 times 3i. I'm just multiplying everything. So I've got 15i times -6i. Well, 15 times -6 gives me, what is that? 15, 30, 45, 60, 75, 90. -90i squared. This is just -1. So I just get 90. Well, what's the pattern, right? We're seeing a lot of I squared. What happens when you get a little bit farther into it and you keep going? Right, so maybe you know it. So I to the 0 power, just like anything to the 0 power, is 1. That's real. I to the first is just I. That's imaginary. I squared is -1. That's real. I to the third. Well, that's just going to be I squared times I, which is -1 times I, which is just -I. That's imaginary. What would happen with I to the fourth? Well, I'm going to take the one before and multiply it by I, right? So I've got -I times I, gives me -I squared. Well, that's -1, so that's -1, so that's 1. Huh, that was the same thing as over here. Okay, let's see, let's keep going. I to the fifth, so let's take this. 1 times I, just get I. Oh, I got that for I to the first. I to the sixth, take the one before and multiply it by I. I times I is I squared. Oh, which is -1. So -1 times I is just going to be -I. Oh, I see a lot of, it's really repeating, right? So what's I to the eighth going to be? If I took this and I multiplied it by I, I'm going to get -I squared, which is just going to give me 1. So this is going to give me I. This is going to give me -1. This is going to give me -I. So it repeats every fourth, right? So first of all, I guess it's good to note that if it's an even exponent, it's real. If it's an odd exponent, it's imaginary. Right? I think that's an important piece to note. It repeats every 4. Right? So like starting with I to the 0. So what if I gave you something like I to the 56th? That's, you don't have to count, right? Let's figure out, let's like simplify that. Right? So let's see, what's 56 divided by 4? 14. Well, it goes in evenly, right? So if it goes in evenly, there's no remainder, so this is actually equivalent to I to the 0 power. So I to the 56th is actually just what? 1, right? What if I said I to the 100th? No, I'm giving you ones that I don't like. Let's say if I did I to the 103rd. Well, let's say I'm going to go ahead and divide it by 4. It goes in what? Twice. That's 8, 23. It goes in how many times? 4 goes into that 5 times, which is 20. And so my remainder is going to be 3. That's where I'm left with. This is going to be the same thing as I to the third. Well, I to the third is just -I. That would be imaginary. Okay? So knowing that simplification. So simplify I to higher powers, right? So maybe this is a good time for you to pause the video and try these on your own. Without a calculator. 20. Oh, didn't I just do this one? 23 divided by 4. It's going to go in what? How many times? 5 times with a remainder of 3. So this is equivalent to I to the third power, which means that it's I times I times I, which means that I have a -I. I to the 101. Well, if I divide 101 by 4, it's going to go in, what, 25 times? And that's going to give me 100, so I'm going to have a remainder of 1. And you don't have to actually do the division. Like, I want you to be able to think through it. So I to the first power is just I. What about 40? Doesn't that go in evenly? That's just going to be I to the 0, which is just going to be 1. 734 divided by 4, it goes in once, that's 4. 33, it goes in 8 times, which is 32. 14, it goes in, what is that, 3 times, which is 12, and so I'm going to have a remainder of 2. So this is the same thing as I squared, which I knew it was going to be real because it's an even number. I squared is just negative 1. Okay. Oh, there you go. Awesome. Okay, so adding and subtracting now. So we want to combine the real components, and you saw this a little bit on the GeoGebra applet. Combine the real components and the imaginary components. So for instance, if I have 3 plus 4i plus 7 plus 2i, I'm going to combine or add the 3 and the 7 and add the 4i and the 2i. Sorry. Which means that I would have, so this first one, I would just end up with, and I'm just going to list them over here. Number 1, I'm going to end up with 10 plus 6i. What about this one? Negative 2, be careful with this minus, so either distribute it or really just make sure that you're paying attention to it, just like you would do if it was x. But remember, I'm just really subtracting 2 numbers here. Negative 2 minus 7, I end up with negative 9. 6 minus negative 5, that's the same thing as 6 plus 5, so plus 11i. What about multiplying? Sorry, I went kind of quick. What about multiplying? So distribute each component of one complex number to each component of the second complex number. This is what we know as double distribution. Okay, you might know an acronym called FOIL. It's an acronym, right? It helps us remember how to multiply, but really what you're doing is you're doing double distribution. So for instance, if I have 3 plus 4i times 7 plus 2i, I have to distribute this 3. Oh my goodness, I like missed. How does that happen? I have to distribute this 3 to both parts and distribute the 4 to both parts. Double distribution. So for this first one, I'm going to end up with 3 times 7 is 21. 3 times 2i is going to be plus 6i. 4i times 7 is going to be plus 28i. 4i plus 2i is going to be plus 8i squared. Okay, so I'm not quite done. I have these two middle terms that I can combine. 21 plus, what is that? 34i. And then 8i squared. Well, I squared, we just talked about how that's just negative 1. So I'm really just doing minus 8. And then 21 minus 8, right? Keep combining like terms. 21 minus 8 gives us, is that 13? Oh my goodness. 13 plus 34i. So I just end up, and that's why when we looked at that GeoGebra applet, I still just have this written as a plus bi. I don't, even though I'm expanding it, it's not written any different. I do need you to be careful that you're not, like, you're using that background knowledge that you know about double distribution, and you're not just multiplying the real and the imaginary parts. You're doing the double distribution. You can't add a real number plus a complex number, but you can certainly multiply them. What about this one? Well, I'm not going to distribute the squared, and either are you. We know better than that. Squaring something means that you're multiplying it by itself. So I end up here with 9, double distribution, distribute that 3, 9 plus 12i, plus, then distribute the 4i, 12i, plus 16i squared. So I've got 9 plus 24i, and I know that this right here, that plus 16i squared, is the same thing as 16 times negative 1, which is negative 16. So I really have a minus 16 there. I can combine those two. 9 minus 16 is going to be negative 5. No, it's certainly negative 7. Plus 24i. What about this one right here? And I know I went 1, 2, and then I'll 3 over here. I think this is my last one of that, yeah. So double distribution again. 3 times 3 is 9. 3 times negative 4i is minus 12i. 4i plus 4i plus times 3 is plus 12i. 4i minus 4i times negative 4i is negative 16i squared. So 9, oh, that's just plus 0. Those cancel, right? And then minus 16i squared, that's like negative 16 times negative 1 gives me just positive 16. So plus 16 gives me 25. So I just got a real number by doing that. Do you recognize this pattern? Well, what happened? So I have a plus bi, and I have a minus bi. And I just ended up with a squared plus b squared, right? And just keep in mind, I'm going to circle what a and b are. A is this number. B is this number. It's not negative b, just b. That plus or minus sign is just there. This is what we call, and maybe you remember learning about difference of squares. I hope. We had something called difference of squares, and maybe you remember working with you if you had something like x squared minus 25. This factored as x plus 5 times x minus 5. Right? The other word for this, and maybe you've heard of this, these are called complex conjugates. So are these, complex conjugates. Right? So if I gave you another one, I'm going to go ahead and just clear my board. And let's say I gave you something that was 2 plus 7i times 2 minus 7i. If I recognize that, hey, these are complex conjugates, so it's a squared plus b squared, I'm in a great place. When I multiply this out, I'm going to get 2 squared plus 7 squared. If you want to check me on that, go for it. I'm going to get 4 plus 49. So I'm going to get 53. You can try it out. It's what I'm going to get. Okay? It's a really good thing to recognize. Two complex numbers, you end up with a real if they're complex conjugates. Amazing. Oh, I did that. So that's really going to help us with our last one over here of division. So division is in parentheses because it's really not division. This kind of sounds familiar, right? It's really simplifying. And the idea is that we really only want, sorry about the animation, we only want real numbers in our denominator is really what our goal is. And so we're going to use complex conjugates and the idea of I squared, because that's just a real number, to get any i's, any imaginary components or imaginary numbers out of the denominator to just rewrite it, right? Like we have equivalent fractions. We do that all the time. That's what we're going to be doing here. So let's see. Here's going to be my first example, 5 over 2i. I don't want I in the denominator. I can't change my fraction. I'm not solving for anything. But what number can you multiply by that doesn't actually change a number? 1. Well, 1 can be written in an infinite number of ways, right? I could write 1 as, I don't know, I over I. When I multiply, I'm going to multiply straight across. I'm going to get 5i over 2i squared, which is going to give me 5i over negative 2. Bam. Pretty cool, right? Whoa, what do I do here? It's not going to help me if I multiply by I over I. That's not going to get rid of it. But we just talked about what you can multiply a complex number by in order to make it a real number. Complex conjugate. You can multiply it by 1. So I'm going to choose negative 4 minus I over negative 4 minus I. Right? And then I'm going to use what I just learned about not matrix multiplication, wow. What I just learned to actually multiply these out. All right, so my numerator is going to give me negative 12 minus 3i plus 8i plus 2i squared. I'll simplify that in a moment. Over, if I remember a squared plus b squared, it's going to help me a lot. I have a squared, and then b squared is just this number in here, which just happens to be a 1. Don't worry about this plus or minus. My a is I have negative 4 squared plus b is 1. It's a plus bi and a minus bi. The b is just that coefficient. It doesn't include that plus or minus. It's always positive. In fact, if it doesn't matter, because if you square a negative, you're still going to get a positive number. Right? I talked about that in the video. So the denominator is going to give me 16 plus 1, which is 17. 17. And now I no longer have that. So now I just have to simplify this numerator. So I've got negative 12, and really this right here is negative 2. So negative 12 minus 2 gives me negative 14. And then in here, negative 3 plus 8 gives me plus 5i over 17. Pretty amazing. So you guys have some practice with this weekend. Make sure that you are working on it and using it, and you've tried it out and you're ready to ask questions when we see you next. But throughout this lesson, we really defined complex numbers and imaginary numbers and looked at simplifying, adding, subtracting, multiplying, and, in quotes, dividing a variety of complex numbers. So really just expanding our knowledge of the number system is really what our focus was. Hopefully you saw a little bit about how this connects with what we studied, what you will eventually study, and you see how this does tie in with quadratics as well, and kind of expanding your understanding on that piece of it too, because you really worked under the real number system in the past. So thanks everyone for watching, and I will see you all next time. If I can figure out how to stop this. Oh, there it is.